All right. Good morning, everyone. And let's talk briefly about the meaning of potential energy in general. We've talked about it in PY105, but it is nice to refresh it. And let's say we have created an electric field in a certain region. Here we have electric field. So what's the difference between having a charge placed here and there? You place it here, and if we use this charge to test the presence of electric field, that's a test charge. So here, no force. Here, there's force. That's the difference. And of course, if we move, the electric field moves the charge, there's some work done in general. And there is always a certain amount of work to be done to bring this charge infinitely far away from its current location. And infinitely far away means there where there is nothing. So there is a natural intention to set the energy at infinity to zero. And potential energy always is measured relative to the chosen level. So if a charge initially is in a field, and no matter how, no matter why, eventually it ends up at infinity, what would the amount of work done by electric field or against electric field be equal to? Well, we start from a certain location. That's the initial location, and there is a certain amount of potential energy related to this. And when we move it at infinity, we wish, and in physics wishing means we define, that's what the definition is, and everybody agrees, that this potential energy will be equal to zero, will be set to zero by us. So in this situation, the work done by electric field will be equal to, so the work will be just equal to that amount of potential energy the charge has when it is located somewhere. That is the work done by electric field when the charge, maybe by electric field, maybe by other means, was moved infinitely far away. And of course, we can ask the opposite question. Okay, if this electric field has been created, but no physical objects still there, how much work would we have to do in order to bring a charge from infinity to this location? Well, so we just switch two things, initial and final. Initial is here, final is there. And the question is about work we want to do. So what do? Well, we take a charge, bring it over here, and place it there. So now, first of all, the work done by electric field on the charge still equals the same difference. We have to subtract final value from initial. And that will be equal to 0 minus u. This is the potential energy of the charge here. But this is the work done by electric field, the work done against some kind of applied force which works against the electric field will be equal to, well, that's due to Newton's third law, will be equal to the same amount, but with the opposite sign. So this is another meaning of the potential energy. This potential energy represents how much work we have to do in order to take a charge and bring it from infinity to wherever we want it to be. That's it. That's what potential energy is. And now we can go back to this question. So what is happening here? Well, initially we have a charge, a 1 coulomb charge placed somewhere, and we know that the potential energy of this charge is 10 joules because that's how much work we did to bring it here. Now we take it out, and instead we're bringing a different charge, 7 coulombs. The question is, what is the potential energy of this charge now at the same location in the same electric field? That's what the question. Questions? So in that case, answers. And this reasoning related to amount of work we use to bring the charge might help, because of course, how can we bring a 7 coulomb charge? Well, we can take 7 coulombs and bring them together, or we can take 7 1 coulomb charges and bring them one by one. First 1 coulomb, how much work done? 10. Then we take a second 1 coulomb, how much work done? 10 more. The third 10 coulomb charge plus 10 joules. The fourth plus 10 joules. The fifth plus 10 joules. The sixth plus 10 joules. The seventh plus 10 joules. So the answer is, this has to be 100%. What it is? By the way, the answers to the so-called test are posted. If you've done it and you want to know if you did it right, you can go to Blackboard and check the answers. And if you have any questions about it, use Piazza or office hours. So two people haven't been listening or guessing or not thinking or absent. All right, you know I can find out who. All right, so of course the answer is 70, because if to bring one charge from infinity, 1 coulomb charge, we have to do the amount of work equal to 10 joules. So to bring from infinity 7, we have to do work which is equal to 70 joules. But this tells us that the potential energy also is a property of two things: a property of this region, a property of this space, and the property of the charge. And we want to define some new physical quantity which would not be related to the charge, it would be related only to the space. And to do that, we invent a new name, electric potential, not potential energy, potential, and we define it as potential energy of a 1 coulomb charge. And why is it handy to have electric potential? Well, because if we know electric potential, which is, again, the energy of a 1 Coulomb charge. We can calculate potential energy of a 2 Coulomb charge, 3 Coulomb charge, 4 Coulomb charge. And how would we calculate the potential energy of a Q Coulomb charge? What should we write? Well, our pattern recognition device, the brain, tells us this is how we now can use that new physical quantity. This variable V might represent many different things. Yeah. The alphabet has only 26 letters, so even with the Greek alphabet, it's not enough for labeling all physical quantities differently. So it could have been volume, speed, Voroshilov. In this particular situation, it means electric potential. And when you write a letter, you must know the exact meaning of this letter in this exact situation. So this is electric potential. That's a name. What's the definition? This. It's potential energy of a 1 Coulomb charge. How do we use it? This. If we know potential, electric potential, we can calculate electric potential energy of any charge. So that's a summary. And in reality, the electric potential is much easier to be measured, to calculate it. So we defined it from potential energy, but we will be using it backwards. We will measure or calculate potential, and then we will use it for calculating potential energy. Well, first stop, how to relate the work done on a charge and this new variable potential, electric potential. Well, all we have to do is just write together two equations. The work done by electric field on a charge equals this difference. But potential energy now should look more like a U. Potential energy now is related to the electric potential. And electric potential might have different values at different locations. If we move a charge from one location to another location, potential energy changes, but it's the same charge, same Q. So this combination of equations tells us how to relate the work done by electric field on a charge and potential difference. Now, can we write it like this? Difference. What do you think? Why? Exactly. We have to follow definitions literally. And by a definition, delta means change. Change always has to be equal to final value minus initial. So, but there's an easy fix. This is how it's supposed to be written. However, sometimes on a website, in some old problem or old textbook, people don't pay attention to little things. They call the same delta different, change and difference. Well, so the equation, and this is what people sometimes forget, this is the equation for the work done by electric field. But if we use our hand to move a charge in the electric field, the work done by our hand is not that. It's the opposite of that. Question, please. That's a problem. You have to solve it. How do you solve a problem? Definitely not by thinking. By writing, consulting with peers, using calculators. So an electron has been moved from a certain location to a different location. The information about each location is presented. We know the electric potential for each point. And you don't have to calculate the actual amount of work. We could. You always have to say, is it going to be positive, negative, or zero? And because a work is a number, these are all the options we have. Well, if we use just real numbers. So at this point, basically this is what you're doing, right? There are two locations. That's it. One you call initial. Which one? Which one do you want? Left or right? Left or right? Okay. So another will be automatically final. So now the initial potential. Everything has potential. Everyone has potential. The thing is how to transfer it into energy. So is equal to 1000. And what I forget to mention, electric potential has a unit. International System of Units tells us that electric potential unit should be equal to a unit of work divided by a unit of charge, which is a joule over a coulomb. But it also has a special name, volt, which is another capital V. So you need to pay attention to the meaning of this letter. And final electric potential is equal to 500 volts. How do we know that? We can read. So now we are applying an equation. We just have to read one more time the work done by or by electric field or by electric field. So we can apply this expression directly. And the initial is 1000, the final is 100. That's equation number 3. We've got a distribution. Number 1 so far is winning, and number 1 is wrong. Again, democracy doesn't work in physics. Why? Is it negative? Why? What do we know about this particular particle, which has a special name? An electron, it's negative. It equals to negative 1.6 times 10 to the negative 19th. That's it. So the work is negative, and actually it's going to be equal to about 16 times 5, 8 times 10 to negative 17 joules. That's it. So when we read a name of a particle, an electron, a proton, normally, we have to know the property of that particle and use it literally. Now, a special case, a uniform electric field. So, in a uniform electric field, when we place a charge in it, it will experience exactly the same force everywhere. So if black arrows represent electric field, and let's say this is a positive charge, force will be pointing in the direction of the field. It might move. We know that work will be equal to this. Well, let's start from but we also know, and we've done it before, that we have it derived from the expression for mechanical work, that for the uniform electric field, potential energy is equal to the product of three values. So we just use this equation. When we write a symbol, a minus or a plus, we have to know the reason. And first minus comes from the expression for the potential energy, but this minus comes from the equation. We have to subtract one number from another. But now we have to write the same equation again, so we have to write a minus, and which comes from a different reason. And equation and equation. And now, well, that's a uniform field, so the strength is a fixed number, constant, same charge. So what is left is this. And this, remember in the picture, was displacement of the charge. But that displacement was measured in a very specific way. In that particular example, initial location and the final location belong to the same line. That's important. So if we have electric field, we have just one line, and we have a charge which has been moved from one location on that line to another location. How? We don't know. Doesn't really matter, actually. The equation doesn't have any information about the process. It only has the information about initial and final locations. And in this situation, the work, well, this is how usually we calculate. The magnitude of this work will be equal to the product of three variables: charge, field, and the distance between the points. Now, jumping ahead a little bit, what happens if electric field is not uniform? Well, even if the electric field is not uniform, we still can choose two locations so close to each other that electric field practically will be the same between these 2 points. So this is a very important equation for any electric field, but we can make an extra step. On another hand, it also should be equal to this from the previous slide. And now, because I use magnitudes to make my thinking easier, I can write delta V. Yeah. And now, because it's the same charge, I can cancel it out. And what we have is a very important conclusion. The relationship between the electric field strength and the potential difference. We will be using this equation for calculating various things and in the lab. How can we use it? Both ways. We can measure potential difference and calculate electric field strength, or we can measure electric field strength and say what will be potential difference between 2 points. But we have to remember these points must belong to the same field line. Otherwise, it might not work. We can go around it, but it's just easier to remember. This equation gives you the direct connection for field potential difference and distance between 2 points when points belong to the same line. How can we get rid of magnitude, absolute values? Well, simple. This is still strength, so it has to be positive, but we just need to make sure that initial potential is higher than final. That assumes that point number 1 and point number 2, which lie on the same line, located in this order. It's like falling down. Well, we're going to have examples. So this is this slide, which does everything. And the summary of this very important connection. And by the way, now we can see that electric field also has another unit. We used to use a Newton over a Coulomb because it's a force over charge, but now it also is equal to a volt over a meter. And of course we can prove mathematically those are the same units. If you make a transition to kilograms, seconds, meters, you get exactly the same expressions. But in different problems, you can see Newton over Coulomb, or in another problem, you can see a volt over meter. You should know it's the same thing. Same thing. Well, so that's a summary for a uniform electric field or for 2 points which are very close to each other. And one more slide with the summary. On the left, it's a reminder how we did come up with all this. We started from calculating the work done on a charge in electric field. And now finally a question. So these lines here show locations with the same potential, electric potential. How do we know it? We don't care at this point. We know we have it measured, and we will learn soon how. So it's been measured that if I have a measuring device here, it will show 20 volts, joule over a Coulomb. So here it will be 10 volts. Here it will be 0 volts. And the question to you is, what do you think about the direction of the electric field? Now, first of all, these lines demonstrate that electric field must be uniform, the same in the whole region. Here and here and here and here and here and here and here, electric field is supposed to be the same. Why? Well, because we can calculate it. Yeah, we will in a minute. If we want to calculate electric field strength, we have to apply this expression. So we have to choose two locations, here, 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 and calculate it. But we know that those locations should belong to the same line. So we have to draw that line. And to do that, well, we could imagine, again, how would a charge move? So let's say I have a positive 1 coulomb charge, and I placed it here, and it's like a ball falling down under the force of, under action of the force of gravity. There is also a hint on this slide. There is also a hint on this slide. On this slide. On all these slides. Those two locations which belong to the same line. Yeah. The first one has a higher potential, and the second one should have a lower potential. So what if we take it to numbers 20 and 10, which is higher, which is lower? 20. So the question basically is, should it be directed like this, or maybe like this, or maybe like this? Because it just can't be directed like that. That would be from low to high. And of course, because the electric field is uniform, absolutely symmetrical, the answer is down. Well, anyway, let's calculate it. All we have to do, just choose any. So that's draw one line. Draw one line. One is enough, and choose any 2 points on this line. Let's say this one and this one. Well, I could have, yeah, probably this is easier. This is my line, and my points B and A, and the potential at point B is equal to 10 volts. How do I know? I can read. The potential at point A equals negative 10 volts. And the distance between these 2 points, which belong to the same line, is equal to, is it 10? No. It's 10 and 10 more, 20 centimeters. But because the unit says it has to be a volt over a meter, we need to convert centimeters into meters. And now we're done. 10 minus negative 10 over 0.2, 200 over, no, 20. 200 will, yeah, 20 over 0.2, 100. 100 what? You can write a volt over a meter. You can write a Newton over a coulomb. Doesn't matter. So, I don't know, I think it's pretty straightforward. We just need to remember the rules. The rules, again, if we use this equation, we need an electric field line, and we have to choose the points which lie on the same line. And the electric potential in the direction of the line drops, actually, yeah. So electric field line points from a higher potential to a lower potential. That helps if we want to calculate actual values. Don't use magnitudes. And since all those kind of calculations use something like this, initial minus final, finance minus initial. Many problems related to a situation like that use different words. So here, in this class, we stick to a definition for the change as a final minus initial, and what we call difference. And that may differ from other definitions. Difference we call larger or higher minus lower or smaller. Basically, a difference for us is the magnitude of change. So always positive number. That's it. So the change, well, it's a number which can be positive, negative, or zero. Difference like distance, never negative. It's a magnitude of that. For example, depending on what's initial, what's final. In this example, the initial value of electric potential is 4 and final is negative 8. The change, negative 8 minus 4 is negative 12. But if the question is what is potential difference, we take a magnitude of that, 12. It will be related to the lab. Well, let's now start solving problems. A negative charge with the magnitude of 5 microcoulombs is placed in a constant, and assumed uniform electric field, released, and the work done by electric field equals a certain number. We know the initial potential, and we need to find the final potential, and etc., etc. Basically, this is what we should say. Find everything. Of course, we start from a picture, right? So please take a minute, draw a picture. Sometimes in the future, once or twice maybe, I will ask you to use your smartphone to take a picture of your picture and email it to me. It happened before, it will happen in the future. It makes my life much harder. I will have to process many pictures. It takes attendance easier. So, I'm not going to do it now, but just be ready. It will happen. So, what do we have? Electric field. So there has to be some electric field. We don't know its direction yet. We know there has to be some potential change. So we should choose the location which we call the initial. And the initial potential, electric potential, is equal to 100 volts. And what we do know is the amount of work done by electric field on this charge. And well, since we know the amount of work and we know the charge and we know the initial potential, we're getting an equation which has only one unknown. Why are you smiling? What does it mean? So what's wrong? Yes. That's potential. Yes? You raised your hand. Yes? Well, that's... No, you raised left hand. No? Yes?
For work
Why? In this situation, the work is done by electric force or field, so we use the right equation. That's the right equation. Yes? How do we know? You can read. The charge is negative. So now we can solve it. First, 5 and 5 is cancelled. -3, -6, we move it over there. So -1000, right, will be equal to 100 minus final. Correct? So final will be equal to 100 plus 1000, yes? 1100 volts. All right. I don't know where it is. I have space here, so that will be my final potential. Now, as we have mentioned, so the electric field line has a direction, and how does it point? It's supposed to point from high to low. It's supposed to be directed from a high potential to a low potential. So this electric field line is supposed to point to the right, well, with my choice of initial and final, from high to low. And what does it mean? It means if we had a charge here, actually, let's make it negative, black, not red. It's a negative charge. And this is electric field. And we know that a force, a charge, and electric field are related by the definition of electric field. And this definition tells us for the positive charge, electric field and electric force parallel point in the same direction. For the negative charge, electric field and force are opposite. So the force acting on this charge from this field should point to the left, and that's why it was moved to the left, because of this force. That's why the final location is to the left, to the initial, because of this force. That's it. So everything matches. And what's next? So potential energy. Okay. For the potential energy, we just can use the equation, which basically is a definition of electric potential. We just use it backwards. It has to be equal to the charge times electric potential. Which one? Well, if we are looking for final potential energy, we have to use final potential. Electric potential energy is negative here, that's 11. So negative 55 times 10 to the negative 4 joules, because that's energy. Let's name it. Okay, final. Now let's calculate the initial potential energy just for the kick. It's going to be equal to same number for the charge times 100. So it's going to be negative 5 times 10 to the negative 4 joules. So we have two negative numbers, yeah, on a scale for the potential energy. How should we mark initial potential energy and final? The initial potential energy is negative 5 times 10 to the negative 4, but the final is negative 55 times 10 to the negative 4 joules, right? So which potential energy is higher? the initial. So when a charge is released, it goes from high potential energy to low potential energy, exactly like a ball when it is released in the gravitational field from high potential energy to low potential energy. Well, I know that there are many, many similar words, potential energy, electric potential, and many, many different connections between them, but there is nothing which can be done about it. It's just a part of our life now. Now, what else? If the distance equals 10 centimeters, calculate the strength of electric field. Okay, that's easy. You just have to convert the distance from centimeters into meters, 0.1 of a meter. And now electric field strength will be equal to, well, delta V over D, 1100 minus 100, 1000, over 0.1, 10,000 volt over a meter. This is the most interesting question. Let's see if I have an extra slide. No, I don't. Okay, so I'm going to add a slide. The last question technically is not related to the new topic. It's the old PY105 topic about energy change. So from here to here, it travels, well, from rest, from no speed to a certain speed. We remember from mechanics we have several approaches. Number one, we can calculate force, because we can. Magnitude of force equals magnitude of the charge times magnitude of electric field, and we know that. And then if we know mass and acceleration, the force and mass, we can calculate acceleration. If we know acceleration and the distance, we can calculate time, we can calculate speed, everything. That's one way. We can use dynamics. Second way is using energy. And of course, no matter what we used, we get the same result in the end. It's a matter of convenience or personal preference. My personal preference here is using energy, because we used potential energy already. We used work. So what else do we know from PY105? The change in the kinetic energy will be equal to net work acting done on the charge. In this situation, that's just electric force which does work. So by electric field. Final kinetic energy, that's what we're looking for, initially 0, will be equal to, we don't even have to calculate anything, it will be equal to that number, 5 times 10 to the negative third. That's the energy already. Now, of course, we can write an expression for the kinetic energy. What was the mass? 10 grams. Convert grams into kilograms. And solve it for the speed. It should be equal to 2 times 5 times 10 to the negative 3 divided by 0.1 square root. Two times 5 is 10. And negative 3, negative 2, negative 2, positive 2, 1. I think it's 1. It's going to be 0.01 over 0.01. That's what I want to believe in. You can check my calculation and correct me. Any questions? Yes? From the text, yeah. I just used it. We used it here, first time, for calculating the final electric potential, and now we used it here by relating it with kinetic energy. All right, I'm going to skip this. So, now we have two means to describe the presence of electric field. Number one, electric field lines or vectors. And number two, now, we can measure or calculate electric potential everywhere at every single location. Of course, there might be locations with exactly the same potential. So those locations we have a name for them. We call them equipotentials or equipotential lines or equipotential surfaces. So for example, for uniform electric field, if we measure electric potential along a line or along a surface perpendicular to field lines, we're going to get the same number again and again and again. That will be the equipotential line for uniform electric field. Now, this can be proved. We actually could do it. It just requires some extra time. I don't want to do that. There is a very simple transition from a uniform field to not uniform field. We just have to break a non-uniform field into many uniform fields. That's it. And this expression tells us how to calculate the exact value of electric potential generated by a single charge. This is the actual value of this charge, which is a positive number for the positive charge, a negative number for the negative charge. That's the same 9 times 10 to the 9 constant. This is the distance from a charge to the location where we're measuring or calculating the electric potential generated by this charge. And our distance for the single charge tells us that at the same distance, electric potential will be the same. So these lines or surfaces in space represents those lines which we call equipotential lines. So this is how we can calculate electric potential of a single charge. In space, equipotential surfaces may look differently, spheres for a single charge. And you see, electric field lines for the positive charge, of course, point away from it. And equipotential spheres perpendicular to the lines. For the negative charge, of course, electric field lines point toward the charge, the other lines. Equipotential spheres perpendicular to the lines. The graph for electric potential looks slightly differently for positive and negative charges. For the positive charge, it's positive. For the negative charge, it's negative, because the charge Q is negative. And if we have several charges, each charge generates its own potential. So if we need to calculate the total electric potential, we have to calculate the electric potential generated by the first charge. Then we have to calculate electric potential generated at the same point by a different charge. And then we have to add them up together. And whatever happens, happens, because each number here may be positive or negative, maybe even 0. The result also may be positive or negative or maybe even 0. And now we just have to do an example. This is a dipole. We know that it's a very convenient system to measure electric field, but it also generates its own magnetic field. So we can calculate electric potential, well, technically anywhere. Yeah? If I pick a point here, what do I need to know? Well, I need to know this distance, call it R1. I need to know this distance. It has to be straight line. Call it R2. I need to calculate V1, K Q1 over R1. Then I need to calculate V2, K Q2 over R2. And I need to add them up together. That will give me the net potential. Bless you. So let's take a point, I don't know, B first. At point B, the total potential will be equal to K times 8 times 10 to the negative 9 divided by 0.4. Now, I want to stress the difference between the expression for electric field strength and electric potential. For the electric field strength, first, we have to use the magnitude of the charge, and secondly, distance is squared. That's it. But for electric potential, we have to use the actual value of a charge. And second charge is negative. And we have to use the distance, not distance squared, which is, again, 0.4. And if we add them up, we can see 0. Actually, if you remember, the electric field strength was not 0. It was strong. It was directed from a positive charge toward a negative charge, but the electric potential there is 0. And then what's going to happen if we move, let's say you have a special measuring device to measure a potential, which has a name potentiometer or potentiometer, using old slang. So if you hear and you measure 0, and then you walk to the right or you walk to the left, from 0, if you're getting closer and closer to a positive charge, your potential will be positive. But if you get closer and closer to a negative charge, your potential will be negative. And of course, we can calculate it. So let's do it. Point A, 9 times 10 to the negative 9, 10 to the positive 9, that's the constant, times 8 times 10 to the negative 9, that's the charge, divided by the distance from the charge to point A, point 2, plus same constant, a negative charge, but the distance now will be equal to 0.4 and 0.2, 0.6. So it will be positive because the second number has smaller magnitude. And what will the net potential be equal to? 240. All you have to do is just take a calculator and finish your calculation. And of course, if you have more charges, 3, 4, you just have to repeat the same strategy again and again and again. So this is how electric field lines, which is red, and equipotential lines, which are blue, look like for a dipole. How did people find it out? Well, calculate it by calculating. Yeah. You can calculate electric potential everywhere, just like we did. And you see that there are lines where the electric potential is the same. Now, this is a positive charge, this is a negative charge. When we are close to a positive charge, negative charge practically doesn't matter. So we should have electric field just very similar to a field of a single positive charge with a positive potential, lines almost straight. And when we are close to a negative charge, the positive charge doesn't matter anymore. So we have lines which are almost similar to the lines of a field of a single charge. But here, electric potential will be negative. There is a line, not just a point, a whole line where electric potential is equal to 0. The question, if you look at this picture, you should choose, this is the question, you should choose your answer, which potential is higher or lower or maybe equal. Here, we're measuring electric potential number 2, when we read on the potentiometer certain number. There, we measure potential number 1, another number. So if you need to compare two numbers, you have to think about electric field. Why is it important? Well, for example, the next question, which you don't have to answer, is about work. And we know a work done by electric field is equal to the product of the charge and potential difference. Unfortunately, in mathematics, there is only a symbol for change, delta, but there is no symbol for difference. So in this situation, we are moving a proton from this point to that point. And we know that the proton has a positive charge. So now, first of all, you see that initial and final is not always the same as 1 and 2. 1 and 2 here are just counting numbers. That's the first location, that's the second, but turns out the second location by counting in this situation is initial for the process. So we should write this difference. And now, depending on your answer, this difference may be equal to 0, positive or negative number. Hence, the work will be also 0, positive or negative number. So, and the answer is, well, first of all, it's very good to remember those blue lines represent locations with the same potential. That's why we call them equipotential lines. So here and 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 here, here and 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 here, the potential is the same, equal V1. Now, this is the equipotential. I want to here V1. This is the equipotential line which goes through both points, and as we know, electric field line points from a higher potential to a lower potential. When we move away from a positive charge, electric potential decreases. High, low, higher, lower, answer 2. And that tells us, in this particular situation, the work will be positive. The work done by electric field. Well, so what is so good about equipotential lines? If I move a charge along it, I don't do any work, electric field doesn't do any work. So first, let's finally prove that electric field lines are perpendicular to equipotential lines. So let's say I have moved the charge like this from point, or like this, from point A to point B. How do I calculate the work? Now we know it has to be equal to product of a charge times potential A minus potential B, but according to a definition, we have chosen all these points that potential is the same. That will be equal to 0. Difference is 0. However, we could have used an expression for mechanical work, force, displacement, or distance, times cosine of the angle between force and displacement. The force is not 0, because electric field is not 0. And distance clearly is not 0. So in order to the same work to be equal to 0, cosine of this angle must be equal to 0. Which means this angle must be equal to 90 degrees. Which proves the fact, finally, that electric field lines and equipotential lines must always be perpendicular to each other. That's it. It's a very convenient piece of knowledge because we can use it to map electric field. How? Well, these are the rules. This is just a summary. How to relate electric field strength and potential difference, etc., etc., etc. The electric field always points from a higher potential to a lower, and electric field lines always perpendicular to equipotentials. So what can we do? This. This is can I actually spread it? I don't know if it helps. You can look at the screen, you can look at the bench. This is just a standard low voltage power supply. And this is so-called conductive paper. It is conductive, it's carbonized. The carbon is a conductor. And this is what people used to call a potentiometer. Now we call it voltmeter, but because this device, just ignore it. Because this device also measures other things, we call it a multimeter now. Now, what do I have to do? First, I have to turn it on. It is on. Now I have to turn this on. Now, so I have to check my scale, okay, volts. Now I can measure. What can I measure? I can measure potential difference between any 2 points. Negative 3.82. Can I make it positive? Of course I can just switch. So here, what can I do? Well, I can set to 0. And normally we set to 0 the ground terminal. I can set it to 0. And this is the lower black, black to black. So, and now I can measure electric potential relative to this point 0, 5.7, 7.3, 9.8, 15. But what I can actually do, I can measure potential and find locations with exactly the same potential. For example, let's take this one. About 5, okay. So next one. Over here. 5 again. 4.9, close enough. So if I connect all these locations with exactly the same electric potential, I've got the equipotential line. And now I can find another one. 6. Oh. 5.9, good enough. 6. This is my second equipotential line. And I can continue and continue and continue. What can I do next? I know the connection between equipotentials and electric field lines. For example, I know lines must be perpendicular and actually wrong direction. Yeah, 5, 6. Electric field should point from high to low, so that's the direction of the electric field. How do I calculate the strength? I can take a ruler and measure distance and calculate E will be equal to delta V over the distance. That's it. That is how we can map the whole electric field just using the potentiometer or voltmeter. Could I explain why? Because it's always high to low. Electric field line always points from a higher potential to a lower potential. Now, just a sec. You can imagine that you have placed a positive charge here and you let it go. If you release it from rest, because it's a positive charge, the force acting on that charge will point in the direction of the field. So if you wait like a second, so it will be moved along the line to a new location, and the work done will be positive. If we calculate the work as force times distance traveled times cosine of 0 in this situation, when both points are very close to each other, when D is close to 0, any field looks like the uniform electric field. So that is definitely a positive number. But on the other hand, we know that the same work should be equal to Q times V initial minus V final. And because we use the positive charge, and this work has to be positive, that means the initial potential has to be higher than final. That's it. Always. So we just use this fact now as a rule. Electric field line always points from a higher potential to a lower. How? We can use it backwards, forward. So if I know a line and I look at 2 points on the line, I know this potential should be higher than that potential. Or if I know 2 points and I know that this potential is higher than that potential, I know line should point like that. All right, so this is how we can map electric field. Now, next step, let's say we have a conductor. It's important that it is a conductor, because if it's an insulator, we can't make electrons freely move inside. But if it's a conductor and we charge it, for example, we make it negative, so we're adding extra electrons, what is happening? They start moving because they repel each other, but they can't move forever. Eventually, they have to stop. And when they stop, of course, depending on the shape, it could be different charge distribution on it. If it's a sphere, the charge distribution should be the same everywhere. And we can add more and more charge. How much charge can we add? Well, or we say how much charge can we store? Well, that's the question we want to study. The capacitance, so the ability to store the charge, depends on many different features. So, for example, what do we know? Let's say we placed some electrons, and of course, if we placed electrons on a sphere, eventually they will end up having equally far away from each other. So electric field will look absolutely symmetrical. Now, what is happening with a different shape? Well, the force acting on each charge, of course, is not just Coulomb's force between electrons. They also have been attracted to the protons inside. Yeah, it's a standard type of matter. Otherwise, all electrons would just fly away. So let's say we have two electrons here. They would repel each other, of course. Well, but in order to hold them together, the protons don't have to compensate the strong force of repulsion. Each actual force can be broken down into two components. One is parallel to the surface, which actually makes them move away, and second, which wants the electrons jump off the surface. So the attraction should compensate this force. And if it's not so strong, it means the electrons actually can be collected, more electrons. But what's important? Eventually, when all electrons stop moving, no matter if we have fewer electrons here or more electrons there, when they stop moving, that means net force has to be equal to 0. And it also means that that force, which initially made them move along the surface, becomes 0, which means there should be no electric field parallel to the surface. There is all electric field perpendicular to it, which means this whole surface becomes equipotential surface, because electric potential now everywhere should be the same. Otherwise, electrons would still be moving. That's the most important fact. If we have a conductor and we charge it, no matter what shape it has, eventually electric potential becomes the same everywhere on the surface, the same. Of course, it's supposed to depend on how much charge we store. More charge, higher potential. So of course there has to be some relationship between the amount of charge we can store and the electric potential the surface has after that. And the actual relationship depends on material, on the shape, on the size. This coefficient, which relates the amount of charge and the final potential on the surface, has a name, capacitance. This equation cannot be used for a dielectric. It only can be used for a conductor. Now, the unit of capacitance should be equal to a coulomb over the volt. We call it a farad, and this is actually a very large unit. 1 farad is a very high capacitance. Normally, when we use electronic devices, we use devices with micro, or milli, or even nano farads. Well, now, again, if you want to, you can prove at home this expression. All you have to do is go back to the slide with two charged surfaces. Write the expression for electric field between two charged surfaces, like this one. Outside, the electric field is practically 0. Inside, it's equal to practically with units density of the charge. So if we know electric field, we know the distance, we can calculate potential difference. So we can calculate how the charge affects potential difference, and then calculate the capacitance, and that's going to be the result. For the parallel plate capacitor, the capacitance is directly proportional to the area, inversely proportional to distance. So if we're adding more area, we're increasing capacitance. Naturally, we give more room for electrons to be stored. But if we're moving away, for example, the plates, so the attraction decreases, and it is harder for electrons to be kept. Now, remember an experiment when I had a charged bat and I used it to move a piece of wood or plastic. And when we were explaining that experiment, we said that by applying electric field to a dielectric, we induce polarization inside it. And as the result, inside a dielectric, we induce a new electric field. Because on the surface of a dielectric, we will have a positive charge. On another surface of the same dielectric, we have a negative charge. So those two surfaces start acting like two charged plates. So there is a difference between a capacitor with nothing inside and a capacitor with a dielectric inside. This picture demonstrates, well, okay, this picture demonstrates the electric field with vacuum inside. And the second picture demonstrates the electric field with a dielectric inside. The electric field due to plates doesn't disappear. But in addition to this electric field, the new electric field now is induced due to the surface charges. So, how do we calculate the net electric field? we have to add them up, the original plus the induced. And the induced electric field is always opposite to the original one. So the net electric field has always strength less than the induced one. Which means we can store more charge in it. Now, if we can calculate the capacitance of an empty capacitor to calculate the capacitance of a capacitor with dielectric, we just have to multiply by a coefficient which has been measured for all dielectrics. It's called the dielectric constant, and different textbooks use actually different symbols for the dielectric constant. Many textbooks don't use a kappa. This is a kappa. They use epsilon. Doesn't really matter. So this is an expression for a capacitance of a parallel plate capacitor with a dielectric inside it. That's it. The air is a dielectric. So when I used the Wimshurst machine, before it broke by a spark, we could store a certain amount of charge in the capacitors, 2 jars. Those not parallel plate capacitors, but still capacitors. And every dielectric can be broken. So eventually, if we put more and more and more charge, if we charge it higher and higher, eventually a spark inside might happen. So every dielectric has so-called dielectric strength. All right, doesn't matter. But it's just a rule of life. Everything can be broken. Well, I think that sentence, everything can be broken, is a good sentence to finish the class today. So we're going to do examples on Monday, but technically you are prepared now to solve at least certain problems on capacitors. Hey, Sonia. Yes.
PY105S, our final exam, is there a way for me to take a look at my
Theoretically, yes. For example, during office hours,